heard today about queries for anti-canonical pairs. Query?
Okay. Thank you. And the talk today, this is the outline. I will first do the Hodge theoretic parts and then complete the proof of the main result. The main result is a Torelli theorem. It's a global one-to-one surjective Torelli theorem. And the proof is constructive in the sense that if you give me the Hodge structure, the proof will tell you how you can hold that variety in your hand. So it has special appeal, I think, certainly to me, in frequently Torelli theorems are nice theorems, but afterward you say, okay, how can you recover the Hodge, the algebraic variety itself from the Hodge structure? This argument will show you more or less an algorithm for doing it. I can find it, yeah. So to explain the result, it's dealing with a rational surface, a smooth rational surface, and an anti-canonical divisor. So an anti-canonical divisor looks something like this, except for where R is the length, and the special cases are these. And it's well known that the pair of algebraic surface and an anti-canonical divisor has a very rich structure. And the point of the talk today is to show that this rich geometry is captured by the mixed Hodge structure on the complement. So the specific objective is to prove a Torelli theorem that mixed Hodge structure suitably marked uniquely determines this geometric configuration. The theorem itself goes back to Leyenga. The specific form of it that I'll talk about today was given by Gross, Hacking, and Kiel, and then essentially refined by Engel and Friedman. And it makes use of ideas from mirror symmetry. It doesn't use it explicitly, but it's again one of those things like in Boudinot's talk where the mirror symmetry suggests some things. Okay. So we're especially interested in the case where the intersection matrix of the cycle, the components of an anti-canonical cycle, is negative semi-definite. The case where it's negative definite means that you can contract that cycle to a singular point on an algebraic surface. And given the singularity of that type, a classical question is, can you smooth it? Can you put it in a one-parameter family where everything is smooth except over 0, you have a singular surface? For a simple elliptic singularity, the condition for smoothability is this. That's a classical result. For cusps, that's the next one of interest. Leyenga conjectured that the condition be that the dual cycle, I won't define it, but associated to every cycle there's a dual one, and it should be an anti-canonical divisor on another rational surface. And he proved this result if the multiplicity is not too big. Okay, so the result itself, let's see, I'll come to it well. The result itself was the Leyenga conjecture was proved by Gross, Hacking, and Kiel, and then a refinement of it by Engel and Friedman. The central result, or the central tool that they use in proving it is the Torelli theorem. So that says if you have two labeled, I'll define that, anti-canonical pairs which have the same, actually it should be H2 of y prime minus d prime, y minus d. No, that's okay. You need an isomorphism of the cohomology of the rational surfaces which has these properties. It takes the anti-canonical divisor to itself. It preserves what I'll call what will be defined to be the generic ample cone. And if the period mapping to be defined agrees, then you can produce an isomorphism of the pairs of the rational surface and anti-canonical divisor. And it's unique up to two things. One is a Bio group element, and the other is a certain finite group. Okay. So the heart of the argument is going to be first to define the period mapping, and then show, given that.
So, Philip, if you drop one or two, then the theorem fails. The Turelli fails.
Excuse me?
If you drop requirements one or two, Turelli fails in these cases. If you drop the requirements one or two.
The top requirement is 3.
Yeah, but if you drop one of these, does the Turelli fail?
He's asking, are all the conditions necessary?
Are all conditions necessary for Turelli in this case?
All conditions are necessary. Yeah. Yeah, these are the necessary and equivalent conditions that there exists such an identification. Okay, so the period mapping from pairs to the period domain to be defined will be shown to be surjective. So coming out of the Turelli theorem and the surjectivity is an existence theorem. Okay. That's what's ultimately going to produce this map rho. This is a Bio group, and this is a certain finite group that is related to the determinant of this negative matrix, and negative definite matrix in that case. So the period mapping, as you saw from the statement, involves choices. The reason for these choices is that there is no canonical polarization in the picture. All right, you have a rational surface, it has an ample cone, closure of the ample cone, things like that, but there's no distinguished ample divisor. So you need some data to replace the role of the ample divisor, and that's what this will play here. Okay? So the general theme of this talk is Hodge theory and moduli, and the Turelli theorem, this one, I think, provides a very beautiful and relatively accessible example of how you can use Hodge theory to study moduli. So the first step is to show that the differential of a period map to be defined is an isomorphism. That, I think, is reasonable to expect because what you have is a log canonic of a Calabi-Yau variety. Right? The pair consisting of the rational surface and an anti-canonical divisor is a log Calabi-Yau. Okay. So the usual proof for Turelli for Calabi-Yau, you can modify it and make it somewhat more explicit. But I think this is what one hoped for the result. The second step, so this is what's involved in the proof of Turelli. And the second step of what one wants to do then is look at the proof of Turelli and let that guide you to analyzing the geometry of this pair and produce the isomorphism in the statement of the result. So first step is the mixed Hodge structure on the complement of the anti-canonical divisor. A labeled anti-canonical divisor just means you give the order. Each of the segments in it is a P1 with 2 points marked. Okay. So an orientation is an identification of H1 of the anti-canonical divisor with the graph. Okay, that's just going around the cycle. Okay. Given a labeled anti-canonical divisor, you have the point at infinity identified with the origin on successive ones. As far as the topology goes, from the exact sequence of the pair, you can find the Euler characteristics are related in this way. And if the intersection matrix is negative definite, which I'll come to in just a second, then the second cohomology of y minus d is going to be b2 minus the number of curves in the cycle. And that's what comes out of this. This is the exact cohomology sequence of the pair. This is what group you're interested in. This has dimension 4, and this has whatever the dimension is equal to the number of cycles, the length, minus the number of relations among those cycles in the second cohomology of the rational surface. So if the intersection matrix is negative definite, you just have the number of cycles, the length of the cycles. Okay. These are the weights. This is a mixed Hodge structure, and it has weights 2 and 4. This weight 4 piece geometrically is the following. If you take the curve, the circle that goes around, the circuit that goes around that anti-canonical cycle, that's in H lower 1, the first homology of that singular variety. That has weight 0 in the mixed Hodge structure. The dual of that would have weight 4, and that's what this thing here is. Okay? If it has weight 4, and it's on the second cohomology, that means that the Hodge type is 2,2. So we need a 2 form. The 2 form is just the form that gives you the identification of this divisor with the canonical. Okay? So there is up to a scale a unique 2 form with first order poles on this divisor. So it's a 2 form having simple poles here. You normalize it by taking the double residues and making them 1. You first take, since it has a pole on these curves, take the first residue, and you get a 1 form on these segments that has poles at 0 and infinity, and you take the residue of that, and an elementary argument shows that those are all the same number. Normalize it to be 1. So to describe the mixed Hodge structure here, we need to describe it in terms of periods. Just thinking of a period matrix, the old-fashioned way of describing a Hodge structure. Okay. So we need to say what the integrals over 2 cycles are. So there's a standard identification which gives you, this is what I just said, that the 2,2 part of the mixed Hodge structure has 1 generator. So that's the thing you're going to integrate. Okay. So it's a 2 form with poles on this divisor. For the cycles, you use this homology sequence. And this is the dual of the circuit, etc. What you are looking at are the 2 cycles in here that have intersection number 0 with the di's for all i's. So those are, if you like, the 2 cycles that live on Y and can be pulled away from D in homology. Now in general, to describe a mixed Hodge structure, where you have pure Hodge structures here, this is the mixed Hodge structure in the middle. These are classified by elements in this X group. So using what was on the previous description, do that. Using what was here, you can track down what this X is, and what you find then is the following. If you take the span of the cycles, or the cohomology classes that are in the orthogonal relative to the intersection pair of the second of the span of the di's, then I'm going to define the period mapping by taking anything here to something in C star. The way you do that is that the second cohomology is pick of y, so you can represent it by algebraic one cycles. It's a rational surface, so it's linear combinations of curves with integer coefficients. It meets each di in degree 0, so you can write it in this way. It's the sum of p's minus q's on the different components. And you take the residue onto the circuit, onto the cycle, and you take the exponential of the integrals of paths connecting these points. So this is what is meant by the periods of the two form with a log pole on D over 2 cycles. So as a standard construction, you can also represent that as integrals over homology cycles, which are pulled off of the divisor. You just do it sort of around each point. You take a tube-type construction. So the theorem is then that the periods, as defined in the previous overhead, give the mixed Hodge structure by this recipe identifying mixed Hodge structures with X's. So I won't go through the argument. This is given in the notes, which are, I think, on the website. But that's, you just unwind the dualities, in Poker duality, and just check that this is the right description for the mixed Hodge structure. So this is what is going to be the mixed Hodge structure that gives the period map. Okay. So the next step here is to go back to the construction and interpret that in terms of the Picard variety of this singular curve, this cycle. So for any line bundle over here, over the cycle, you have a multi-degree. If you take the normalization, that just means you look at the line bundle pulled up to each P1, then you get a standard exact sequence where here, this is just the disjoint union of P1s. There are of them, so it's just the integers R times. This is pick of D, and you just track down what the normalization does. You get such a sequence. You take its cohomology, and denoting by pick naught, the usual pick naught, the things that have 0 in their Chern classes, you get the Abel-Jacobi map from pick naught to C mod Z. And geometrically, what that means is you take a line bundle, it has degree 0 on each of these curves, each of the segments, and each, therefore, it has degree 0. It's some kind of divisor of this kind on each segment, and you take its Abel-Jacobi map. So that's just a restatement of what the period map is. Okay. And this is just checking some of the details. What it means to be in the kernel of the Abel-Jacobi is that there's a rational function on the whole cycle that agrees at 0 and infinity. So it matches those points up. Okay. That's the condition that something be 0 in C mod Z, or the exponential should be 1. So a special case is where the line bundle is not only is represented by a cycle, that's the difference of 2 points on each segment. So you have P1 with 0 and infinity marked, you have 2 further points. That gives you a cross ratio, okay? And these 4 points are ordered, so that's a well-defined number. So that's sort of the character of what the period mapping is. So special divisors of the type we're interested in arise as follows. That you take 2 curves that meet the segment in point P and Q. We're going to see that you get such configurations where these are -1 curves on the rational surface. Okay, curves, the self-intersection -1, they can be contracted to points, but not if you are worried, if you keep track of the divisor D. They're stable under deformations, so these types of configurations map to open sets. The Abel-Jacobi image of this is determined by this cross ratio, and these are the basic curves that we will be constructing, just differences of -1 curves. So where do these things come from? If you have a singularity, contract the cusp to a point, suppose you can smooth it. Nearby, there will be vanishing cycles. Those are homology classes of self-intersection -2. They're two spheres constructed by Picard and Lefschetz many, many years ago. And the limit, as you go into the singularity of these S2s, will split into a difference of two rational curves. Think of the sphere as being the real part of a quadric, a two-dimensional quadric. On a two-dimensional quadric, you have the two generators, all right? The usual picture of a quadric with the lines on it. You have two generators on the quadric. The difference of the generators is what you get in the limit when a vanishing cycle goes into the singularity. So that's the origin. Geometric, it's not part of the proof. It's hard to make this rigorous, but that's what's in the back of the mind about what these configurations are. There'll be one of the other basic curves that you can expect on a rational surface. They're -2 curves. These are curves that contract to a rational double point. We'll see that any such curve is disjoint from the divisor. And the Torelli theorem, the local Torelli theorem is going to show you that since it's disjoint from the divisor, its Abel-Jacobi image is trivial. And that means if the Abel-Jacobi map is onto an open set, that generically there are no -2 curves. And that's what it will turn out to mean. So, so the next step, so now we've described the period mapping. The next step is compute its differential. This is done in almost the exact same way that you do for a smooth K3. Okay. So your pair maps to a line in this vector space. Okay, the line is just the image of this form omega. It's the one-dimensional subspace represented by this differential form with a log pole on the cycle. So it's a line in a vector space. And the intervals here, I've got typos throughout. The r's from here on should be the second Betti number of y minus r. This is the number of parameters that they will depend on. You have to take the second Betti number because you're interested in the cycles on this rational surface y. You want those that have intersection number 0 with these di. Those are r conditions. So this r should be d minus r. Okay. We want to show that this has dimension d minus r and locally maps to the intervals that were on the previous slide here. And so in the notes, there's an argument why this is so. You identify the deformation space. And so this is the tangent with the moduli of pairs with this cohomology. That's a standard Codaro-Spencer type thing. Compute the differential by seeing when you move the pair, y comma d, and you compute the derivative of the periods, you end up over here. It's a line in a vector space, or it's a vector space modulo of this subspace. And so you have to compute these groups. And there is in the notes the computation of these things. It's an elementary computation. It's what you would expect when you do this sort of thing. So I won't go through all of the individual steps here. But it gives you sort of flavor of it. I hope that you have to compute this group, you know what it is. You have to compute this group, and the second group is this is the part of the cohomology of Y. Mapping to 0 here means it goes from here, and this group here is identified by this type of cohomological computation. So you put the various identifications together, track through them, and you find that you have an isomorphism of the tangent space to the moduli of pair d comma of y comma d to the lines in this vector space. They both have dimension equal the second Betti number of the rational surface minus the number of curves in the cycle. The basic identification is looking at the mixed Hodge structure here, the weight 2 part that is of Hodge filtration weight of type 1. So that's first you take the associated weight filtration, and then you take the associated Hodge decomposition, and you identify this group with this thing which appeared on the previous slide. That's really the basic identification. Okay, so that's the first statement, first thing that you use, that the differential of the period map is an isomorphism from moduli to periods. Now you want to prove that it's surjective. Okay. So the theorem is that the anti-canonical pair has a deformation parameterized by some number of copies of C star, and the differential of the period mapping is surjective at that point. It doesn't say how many copies of C star, it just says that there's some copies. Okay. As a corollary, the period map is surjective. Well, why is that? The period map is a map from a bunch of copies of C star to a bunch of copies of C star. Okay. These are affine algebraic varieties. The map is a morphism of affine varieties. They're also algebraic group schemes. It's a morphism of algebraic varieties between group schemes. It's a general fact that any such morphism is a morphism of group schemes followed by translation. Okay. So you only had something that was sort of locally an isomorphism. Globally, it's a morphism of affine group schemes. So the result is that then the map itself that you're only given locally is in fact globally a morphism of affine group schemes plus a translation. So the reason for that is that this morphism here induces a morphism of mixed Hodge structures. The tangent space to the affine group scheme is a Euclidean space modulo the first cohomology. That's what the general fact. And so since the map on tangent spaces is surjective, this morphism of group schemes is surjective, and that's the global existence theorem. Okay? So it uses some algebraic geometry that a locally defined morphism between affine group schemes actually is the part of a global morphism, and you can say it's surjective if it's surjective on tangent spaces. So this is an existence theorem because what it says is that there exist cycles that have intersection number 0 with this divisor, and this should be in a B2 minus R, that's the rank of this lambda parameters. So we want to see what such cycles should be. So this part of the period map tells you that there are enough algebraic cycles that map onto all possible periods. So let's look at what they might be. So the first ones that come to mind, the ones that were mentioned earlier, are exceptional curves. These are P1s that meet the cycle D in a point and have intersection number -1 with the canonical. So they're called -1 curves. So what you get by blowing up a point. It's an interior exceptional point if E, this should be E, it's interior, that this is a typo, if E meets DI star, that is, it doesn't meet DI at 0 or infinity. It's what you think by the word interior exceptional point. It's just a P1 that crosses one of the segments in the cycle in its interior. Okay. So that's the first thing that comes to mind for curves. Second is, again, to blow up some algebraic surface y bar with exceptional curve E. You take the proper transform of B if it's a smooth point, that's the one I just mentioned, that doesn't increase the number of cycles, it just puts the E crossing a segment in. The second kind is that you blow up an intersection point. Okay? And then what you get is on one new cycle, so the number goes up by 1, and you've added a P1 as one of the segments. So that's a corner, if you like, blow up. Finally, what you can do is blow up a point, an interior point, you get an E. Now blow that thing up. When you do that, you get a -2 curve, and E goes blow up of the point. Okay? So the E becomes a -2 curve, and you get an E bar. That's a generalized exceptional curve, so it's a -1 curve crossing a segment in its interior, plus a bunch of -2 curves forming a chain at the end. Now, it's a general fact that for any rational surface, there's a minimal rational surface given by a sequence of blow-ups. When you do the classification of surfaces, when you classify rational surfaces, you prove that by eliminating all the -1 curves, you get either P2, P1 cross P1, or P1 bundle over P1, the Hirzebruch surface. So if we just blow down all the -1 curves, you know what you get. So what about our rational surface with this cycle D? Well, if we forget about D and blow down all the -1 curves, we know what it is. So start with one of the standard minimal rational surfaces, P2, P1 cross P1, or Hirzebruch surface. Choose an anti-canonical divisor on that. You know what those are. For each one, there's 2 or 3 possibilities. And now go through this blowing up process. Blow up interior exceptional point, blow up interior points to get an exceptional curve that crosses the interior of a segment. Blow up ones on the corner point, or do these generalized exceptional curves. So whatever your rational surface is, it's obtained from a short finite list of original rational surfaces with anti-canonical cycles by blowing up. Okay. So here is our algebraic surface, y comma d. Down here is the minimal thing. And start varying all the interior points that you blew up. Okay. If you go through the proof of the local Torelli, you'll find that by doing that, you locally map onto all the periods. So this is not a unique construction, but it's a surjective, locally a surjective construction. Okay. So here's where the algebraic geometry comes in. You know what any rational surface is. Now refine how you prove what it is by putting in the anti-canonical cycle and see what happens to that thing as you go through the successive blow-ups to construct the rational surface. Then just keep track of the interior points that appear in this process, let them vary, and go back to the construction of the period matrix, and you find that that map locally is onto. So that's the argument that the local Torelli period map, the local period map is surjective, and then the earlier argument about group schemes shows that that globalizes. Okay. So now we know that the Torelli map is surjective. The remaining step is to prove that it's injective. Okay. So you have to refine all that you've done to say that if you have two rational surfaces with anti-canonical pair, two rational surfaces with anti-canonical divisors, if their periods line up in a very special way, then the surfaces of the pairs are isomorphic. So this now brings us to the proof of Torelli, the first steps. This is just a restatement of the theorem. Two labeled anti-canonical pairs, isomorphism of the second cohomology. Yes, that should have been in the original statement, the second cohomology of the pairs. I'm sorry, this one here should just be y prime and y. And the pairs map to, or the pairs map out gamma of d prime as di. So it's again a typo. Take out the d here, make this d prime. I'll explain what this is now. Then the period maps should line up, because if you have this property here, then you get a map of the pairs. Then there is an isomorphism unique up to notations that will be explained. So we're going to show that the data given above is enough to reconstruct the geometry of this anti-canonical pair. Okay. So because of the local Torelli, you have a mapping between the moduli space, the period space. They're locally isomorphic. Okay. So if you can prove that generically they're one-to-one, okay, so that means you take out a bunch of subvarieties where exceptional things happen, and if what's left, they're one-to-one on that, then they're globally one-to-one. Just a general statement. If you have two smooth algebraic varieties, not compact, but two smooth algebraic varieties, and a morphism between them, which when you take out a countable union of subvarieties is one-to-one, then it's globally one-to-one. If it's locally one-to-one, it's globally one-to-one. So it's enough to prove the Torelli for taut pairs, that is, well, it's enough to prove when these are generic. So a taut pair is one that's determined by the intersection sequence alone. You just give that sequence of numbers, and then you get y comma d. Then if you have two taut pairs, so that's the same thing as saying that the local moduli are trivial. Okay? Doesn't mean that they're the same, but it means that locally they don't vary. So if you have two taut pairs, then the result is true, the global Torelli. And there what you do is you classify taut pairs. There's a short list. You know what the y must be, P1, P2, P1 cross P1, Hirzebruch surface. And you know what the anti-canonical divisors must be. In each case, there are one or two choices. And you just look at the list and check it. That's the way the proof goes. So the construction of YD and YD prime from taut anti-canonical pairs, when you do that construction by blowing up, you increase the Picard variety each time because you're putting in a new line bundle, new algebraic curve. Okay. And this suggests an inductive argument on the rank of the Picard variety. It focuses on the role of the interior exceptional curves, excuse me, because the period map doesn't see curves that don't meet the anti-canonical divisor. Okay. So a -2 curve, that's a P1 whose self-intersection is -2. And it's not one of the components of DI. By injunction, you find that it doesn't meet D, because C squared is -2, this is 0, so D dot C is 0. So any -2 curve doesn't meet the anti-canonical cycle. Now, I said earlier that a -2 curve, the period map doesn't see that, because for the period map to see an algebraic cycle, it has to meet D. Okay, just if you go back to the definition. So if it doesn't meet D, the period map doesn't see it. So if you have a -2 curve, it's 1 in that product of group schemes. Since the period map is onto, what that shows is that the generic pair, Y comma D, doesn't have any -2 curves. Okay. So that's how you're going to get a handle on these -2 curves. So next, if you have an irreducible curve with C squared negative, then it's either a -2 curve, an interior exceptional curve, or a component of D. And that's, again, the proof for that is just the injunction formula that I used at the previous overhead. So a generic pair are ones with no -2 curves, and what I just argued was that this definition is justified. So the pairs that have -2 curves are the complements that have, it should be pairs having no -2 curves lie in the complement of a proper subvariety in the deformation space. Okay. So for the next step in the argument, we'll look at the elements in the second real cohomology whose square is positive. The ones whose square is negative, where is that? Yeah, the ones whose self-intersection is negative are taken care of here. So we have to worry about those which have positive self-intersection. One component of this contains the ample cone. So you look at the closure of the ample cone in C+. It's not the same as the closure here. So those of you who've looked at Morey theory, the cone theorem and things like that, that's what's going on here, is the arguments related to the cone theorem in the minimal model program. So you take this closure, and the provisional definition then is that you take this closure for a generic pair. Okay? So you take out a countable union of proper subvariety, and you take this thing here. That's the provisional definition of the closure of the ample cone. So the final steps in Torelli are to go from numerical data to geometric data. So I'm just going to give a sketch of how that goes, sort of give the flavor of it. So if we can get everything down to numerical data, so instead of -2 curves, we're looking at cohomology classes of square -2, okay, which have intersection, which intersect 0 with the canonical of P2. Okay? So that's numerical as opposed to geometric. So if I get everything down to just numerical data, then it's going to be that inductive argument that I mentioned to complete the proof. The things we have to worry about are classes whose square is positive. The negative ones we dealt with. Okay. So a numerical exceptional curve is what you think it is. It's effective if it's the class of an effective divisor. That doesn't mean that it's a -1 curve. It could be a linear combination. Okay. I mean, that's going to be hard to happen, but you have to be careful in some of these arguments dealing with the closure of the ample cone. So it's an effective numerical exceptional curve if and only if these two things happen. And this is sort of a typical type of argument you use for these statements. So what we're doing here is to go from numerical data to geometric data. So we have a line bundle, use the Riemann rock and just the elementary argument from the Riemann rock theorem that produces the effective -1 curve. Okay. So then, if there are no -2 curves, then you identify the effective numerical curves numerically. I mean, geometrically. So this is how you go from numerical data to geometric data. So this is the formal definition then of the generic ample cone. And since it's given to you by numerical data, it's invariant under monodromy. So the statement of the theorem at least makes sense. Okay. You've got, what in the Torelli theorem, you've really only given numerical assumptions. Well, you've given that the Hodge structures line up plus some numerical assumptions, and you want to produce a map. So the next step is to look at the characterization of this closure of the ample cone and relate it to the generic ample cone. I'm not going to give that argument. It's very similar to the one I just gave. It uses the Riemann rock for surfaces, which is it's very easy to use because the canonical is negative. So a lot of the cohomology tends to drop out much more than it does for when the canonical is positive. The last element is to deal with the -2 classes. So given a class whose square is -2, then you can define a reflection. So those of you who studied singularity theory, you remember that you have the Dinkin diagrams, and each node on a Dinkin diagram gives you a reflection. That corresponds to -2 curves. Or, I'm sorry, that corresponds to vanishing cycles. So that's what one has in the back of one's mind, that the -2 cohomology classes should be vanishing cycles. Each one gives you a reflection on the cohomology. That's going to be eventually turn out to give you the vowel group part of the argument. Okay. So these are the reflections in the class beta, or the wall. And for a -2 curve, the generic closure of the ample cone is invariant. And the argument is that first, the reflection preserves the intersection form, it preserves DI, so it suffices to show that it produces the class of numerical exceptional curves. If that's clear, if you go back to the definition, because everything is numeric now. So that gives the definition of the vowel group, is the group generated by reflections in the set of -2 curves on Y. And these arguments that were just given shows that this closure of the ample cone is a fundamental domain for the action of the vowel group on the generic closure of the ample cone. So the difference between the closure of the ample cone and the closure of the generic ample cone is a vowel group element. It's a finite group. So now, this is again numeric. You have a cohomology class with square -1. It's a root if it preserves this. And we want to identify the -2 curves among the roots. They're not all the same. That's the subtlety in the argument when you try to track down the details. So the basic result is to identify the -2 curves among the roots. The left-hand side are the roots. Those are -2 cohomology classes. The right-hand side gives you basically the statement that if this beta is not a -2 curve, you can deform the pair where it becomes a -2 curve. So a root satisfying this condition, it preserves the generic ample cone, can be deformed into a -2 curve. So the final existence theorem in the proof then is given an anti-canonical pair and a root with 2 exceptions that are given in the references there. There are disjoint exceptional curves such that beta is the difference. So you're looking at very general deformations, and what you're saying is that for any -2 cohomology class on a very general deformation, it's the difference of 2 exceptional curves meeting a segment. And now you're basically done, because like I said, it's enough to prove the global Torelli theorem for generic pairs. For generic pairs, we've really gotten rid of all the curves on Y that we didn't know about. And now you use that induction argument. You start with the minimal models, and you build up your pairs by blowing up. So you have a YD and a Y prime D prime with the same Hodge structure. And each one, you can contract one -1 curve and drop the rank of the Picard by 1. Now use an induction assumption. You look at the period map for the thing after you contract the -1 curves. Everything will line up. So by induction, there's an isomorphism of those pairs with 2 -1 curves contracted. And now use again the fact that the Torelli map picks up the point that you blow up when you take a blow up, an interior blow up. So that final step then, again using just what the period map is, tells you that the pairs are isomorphic. So the way I think of the proof is that you first get in mind the Hodge structure on the complement, and how it relates to the geometry of the curves that meet the anti-canonical cycle. We first think of the obvious curves that meet the anti-canonical cycle, the exceptional curves. Okay. The -1 curves, you don't have to worry. Yeah, they're the -1 curves, either it's an interior one or a corner one. You're really interested in the interior ones. But you've also got curves with -2 cohomology classes, -2 curves. So you have to deal with those, but those occur non-generically. So now you've sort of dealt with the curves with negative self-intersection, either -1 curves or -2 curves. You look at the ones that have positive self-intersection. That's where this generic ample cone comes in. That's what keeps track of those. So essentially you're using, if you like, the geometry that you infer from the nature of the period map to reconstruct the configuration of curves, or of exceptional curves on these pairs. So this is the global Torelli theorem. And as I said, this is the main tool that's used by Gross, Hacking, and Keel to prove the Loyengo conjecture. One last remark about the Loyengo conjecture. How do you define the dual of a cycle? Okay. So this is very interesting. What Loyengo found was that whenever you're given one of these cycles, there's what's called an Inoue surface. It's one of the Kadara lists of a non-algebraic, non-Kähler surface. And on the Inoue surface, any cycle of -1 of rational curves has a corresponding dual cycle that also occurs on the Inoue surface. So the proof of the theorem about smoothability of cusps, all proofs go through the use of the Inoue surface, which is a non-algebraic object. So there's no way you're going to prove this theorem with current argument in a purely algebraic setting. The Inoue surface is very interesting because it has on it its canonical divisor, or minus the canonical divisor, is the sum of d and d prime of the cycle and its dual. And Loyengo proved that each of these deforms separately. And if you deform it, smooth one of them, what you get now is an algebraic surface with a cusp on it. That's a rational surface with an anti-canonical cycle. So that's how the Inoue surface gets in, that the anti-canonical cycles and their duals occur in pairs on Inoue surfaces. You can smooth one of them, and that Inoue surface becomes an algebraic surface with an anti-canonical divisor. And then you go back to this Torelli type theorem to complete the argument. So far, that's the only proof of the Loyengo conjecture. And that then gives you the criteria for smoothability of cusps. And it's, it's really quite subtle because the length of the cusp can get very big. Just in simple examples, it will be a large number. Okay, thank you.
So does the connection with mirror symmetry go to these Inoue surfaces?
No, it uses that, but it goes deeper.
No, but they are not Kähler, and so it's kind of...
I mean, that suggested that for each Y, D, there's a mirror of some type. And that, I think, that is not used, the mirror is not used, but it suggested that for each Y, D, there's another one somewhere.
Even if Y is not algebraic?
Yeah, it's not algebraic.
Other question?
Yeah.
Excuse me, can I ask, what about recent development of hot theory over non-Archimedean fields? This probably over complex fields, over real fields.
So far, this argument is, you can formulate, it's interesting, it's a good question, you can formulate the hypotheses over, I think, the characteristic zero algebraically closed field. Because the period map, as it came here, really reduced to looking at the usual map of Picard, the usual hot structure, or the usual period maps for the Picard group of an algebraic curve. So that you can do algebraically. So you can formulate the argument algebraically over a field of characteristic zero. But the argument as it stands now certainly uses the complex numbers for this global Ferrari part of it. That's a good question. And if you want to smooth cusps, then you can't even just use a complex number for you can't use algebraic geometry even overseas.
Question?
I have a detailed question. So you define the generic ample cones for Y. So this guy depends on the pair or just depends on Y? The generic ample cone.
So what does smoothing mean? Yeah, it's a good question. By deformation of the pair, I mean it's deformation of D1 up through DR, that whole configuration. But there's also deformation of Y, D. You don't label all of those. That means that allows you to partially smooth. So what that's getting at is what was really the question that was on the singularity people's mind, I think, is what are the adjacent singularities to a cusp? So those are the ones where you partially smooth the thing, the adjacent singularities. And how do you get your hand on those? That was really, as far as I can tell, I'm not an expert in this area, but that was really the question. Well, they wanted to prove the Young conjecture, but they also wanted to give a description of the adjacent singularities to a cusp.
Okay. And also, you said that the generic ample cone is a fundamental domain of the ample cone.
That's right. Yeah.
And it's under the group action. So that group is a Lie group or is it just a group? It's a Lie group.
That I'm not sure.
Oh, okay.
Okay.
Thank you.
If you look at in the references, there's the expository paper by Bob Friedman, and that sort of thing is in there. I just don't recall.
I thought it was typically a discrete group. I thought it was typically a discrete group, maybe even sometimes an emphatic, like the opposite of the group.
Could be.
This wild group generated by reflections.
Yeah.
Is this the group we're talking about?
Yeah,
It's,
but I'm not sure.
It's
Because
discrete,
vowel
not,
is-
yeah, no, if I said it's finite, that's wrong. It's not finite.
No, but I mean, I think it's still a big discrete group.
But this was the question, I'm not so sure. All right,
Okay.
let's thank Philip for that. The next talk is an applied math talk. Philip, you will